If you don't need them, we don't use them. This is another lower floor. This is, yeah, so this is where you see this transfer of the core. Right now we are at the 7th floor with the amenity space. We have a pool on the south side. This is a pool space. And we started to transfer our main structure in the tower right above the MoMA museum space. Yeah, so this is the museum space that MoMA uses today. This is the extension of MoMA. This is attached to MoMA Museum, which is east side of it. So this is a view of the structure, basically. This is our trigger floors. As you see, we allow openings in here for the mechanical space. We allow them to use the whole space. So this is not, didn't create any additional mechanical requirements. We work with the mechanical engineer for the openings, and we provide them the necessary openings that they needed throughout the building life. So this is a view under construction. This is a view from the floors, lower floors, but this is basically the steel transfer floors that we transfer the core above the MoMA space. We did this in steel because it's faster. You could have done it in concrete. Steel was faster. We provide options to client contractors, and they decided to go with this. So we provide. So this is a drawing. And this is actual construction. So majority of these items are pre-assembled and they transfer to the job site. This is one of the example of early planning sizes, tolerances, and exact construction schedule. That's where the difference starting to make it. As you see, all these buildings are standard. They are standard because there's no floor area. There's very limited floor area. So you try to structure a building doesn't require too many people at the same time on the field. But in another way, it has to be in synchronized, it has to work like a clock. So this is another view. Okay, so it looks like it's overlapping. Okay, so the other thing special about this buildings are the nodes. Nodes, as I told before, we advise the client to cut the cost to do a still perimeter diagrid system, but they didn't want to have it because of the monetary constraints. And architect insisted of having all the diagrids. Although all the diagrids here you see in this picture, in this here, although all these diagrids are concrete, there's additional diagrids are there, which architect wants to just put in the building. So we didn't use them because we didn't want to make the structure more complicated, create more nodes, which is these diagrids connect. There are some diagrids, there are 8 connections comes to the same point. You know, when the forces are too high, the space is limited, and you have to provide a speed construction. These are very important items. And with all this complexity, let me repeat it, we did a 3-day cycle for this building. So in this one, you see, whenever it's red, these are, if you go to see the building today, you see a line here, these lines, in the facade, but they are not concrete. This is what the architect insists to have in this. What we have is the blue ones. We place the diagrids where we need it, where we think that it's efficient, just to reduce the degree of complexity in the structure and the constructability. We want to increase the constructability on the structure. So this is how we approach projects. We engineer and detail almost every element ahead of time. We have to make sure that it fits, it's buildable, and it works. So we provide several options to ownership and the contractors, how they can build the corners. This is a final element analysis for the modeling that we did extensive analysis for the interactions. These are the nodes that we finite element analysis. We did the finite element analysis. These are early details that we provide to the owner just to understand what they want to do, how they want to do. And this is basically what we ended up with. So what you see here is when the connection is so complex, we provide a steel node in here. So this steel node is pre-assembled, and everything is, I will show next slide. This is pre-assembled in the warehouse and is shifted to the field. And with this detail, we still managed to get 2.5 day construction schedule. Here, this is a mock-up. So what it means is there is a warehouse close to the job site, and we build this. This is before the project, just to see how can we make this physically, people work it faster. This is one of the very complicated nodes. And we build this, and we get some comments from the ownership, from the contractors. But all these connections that require steel connections, which is generally at the bottom of the building because you have high forces. At the top of the building, these diagram sizes are really small, and it's not that none of the requirements we have this steel nodes. This is installment. Okay. Okay, we're supposed to, yeah. This is a 432 Park. This is basically a repetition of the, since is a different type of element. So in this building, we will talk a little bit later. Let me see. So in this building, because of the shape, as you can imagine, the wind was very high, and the wind forces on the structure was very high. So they didn't want to change the shape because of different reasons. And what we offer them is, when you see the red floors, these are mechanical floors. This is a typical floor plan. This is a concrete shear wall and perimeter spandrel beams, columns. So what we offer them is this solution. So this is a mechanical floor, and this is what we call a drum. So what it means is here everything is exposed and open. This allowed the wind travel through the building and reduce the wind effects on the building. This saved a lot of money, and we were able to reduce the sizes. Although we have this, we are able to do an outrigger floor. We are able to connect the core to the outside columns to stiffen the building up. Okay, this is another drum, and you see the outrigger connections. Yeah, this is allows you to go through. This allows the wind to go through the building. This is 157 West 57th Street. So this project, as I said, this is a very small project, and we had a lot of thinking process. We put up front the building. So what the south side of the project basically, just one second. Yeah, south side of the project sets back along the building. And one of the early designs, there was we were thinking about they put a column, but at the end of the day, we removed the column just because we want to give more freedom in this area, because there's no space. And in north, all this, we have only 2 columns throughout the project. The rest of it is side walls with openings in them. And above the project, top floors, we started to reduce the length of these sidewalls. This is an outrigger floor, and we had 4 here. This is a section of the outrigger floor. So again, main design considerations, we early on engaged the wind tunnel, especially when you do very special structures like this, you want to get wind tunnel input early in the game. Also, it's a common known fact today is wind tunnel, the code doesn't address the wind loads on the buildings very correctly. They don't address it dynamic component, they don't address it location, they don't address the geometry. There are a lot of things that they don't address. It's basically when you have a building that this significant, you want to have a wind tunnel and you want to have a wind tunnel early in the process. So there are some cases we ask the client to entertain the idea of changing the shape. Changing the shape is basically outside, if you do it outside, you put, say balconies to confuse the wind, just to break the wind. Or in this case, they want to have the same shape because they don't want to do additional construction of the shape. They just want to have the basic form just going up, which is 2-day cycle. In this case, we asked him if there is a possibility to have the open floors. Architect liked it, owner liked it. There is no problem with the building department at that time. And it moved on. The job is progress. Although we had a 1,400-foot tall building, we have very successful, reasonable sizes, if you can imagine. Yeah. So also in our projects, we look at the comfort criteria, and we have a very good understanding of buildings in concrete buildings, all the steel buildings, tall buildings. We have been where we are with all these years of experience in high-rise buildings. We have extensive data. So we understand how the building works, and we understand what we should expect when it's constructed in a certain way. But this requires also a very strict observation of, especially the concrete building, what kind of materials that you put in the building, what's in there, what's the result of this. Since these buildings are doing 2 days, 3 days a cycle, if there's a problem, the time you catch the problem, which is say 7-day cycle, 7-day breaks, it may be a little late. So we want to be in charge of with all these materials. Although we push the materials, we put special regulations when we define the materials in our buildings. This is very well explained these phenomena before. I'm just going to go through. Vortex shedding is a very big problem in rectangle buildings. And also when you do wind tunnel, you want to have existing conditions and future conditions. It's very important. You want to know who's going to build, what's going to impact on your building. Buffeting is another common problem in tall structures, especially at MoMA we had an issue because of the 2 towers that you see on the right side. So this is a wind tunnel for 432 Park. Yeah, these are the open drum floors that we have the circle. Get the wind move. Also, there's another thing that we did on this project, and we look at that option also. Sometimes although you figured out that you need a damper in the building for comfort criteria, you don't have to address the whole thing with a damper. So we also look at other options, or sometimes a combine of 2 options. One of the options that we look at is if we can increase the mass of the building to the top, which is a generalized mass. We try to increase the generalized mass to address or reduce the acceleration issue. So we have, like in this one, we have 2 mass dampers, and that time it was the biggest one. Added up, now we have 270 and West 57 is the biggest one. So this is another wind tunnel test. So we were engineer of this tall building. So we tried to, in this one, we tried to see what's the impact of the other buildings on MoMA if there's any. So you see this is the MoMA tower under test. This is 111 and this is 217 West 57th Street. This is the top detail of 157 West 57. This is a wind tunnel representation of how we let the wind flow in this building. We have multiple opening floors in this one. The client wants to have some level of, say, balconies because the code doesn't allow you to go to full floor opening. So there's a parapet in there because of the code regulations. But these floors are open and these are attached to the triplexes and the duplex units. Some of the duplex units is throughout the building. They have open floor utilized as terraces. This is a wind tunnel. I'm just going to go. So these are the floors where we have the open floors. We let the wind go on top of the open floor at the top, the steel structure. So we also employ on these special structures dampers, and there's dampers that we employ today are all passive dampers. So, but we're also looking at options to do semi-active dampers. But the knowledge and expertise and the data is quite good today. We have quite good data that these systems are, auxiliary systems are working. They're working very well. And we look at different criteria. We look at 10-year, which is a North American criteria. We also look at 1-year criteria. It used to be 5-year, but now they changed it to 1 year for ISO criteria. This is a period-dependent criteria. On top of it, starting with the super slender tower, we started to look at 1-month criteria, which is the wind event that you will experience a lot. So another damper is in the 56 Zener. So we have a slush tank in there. Once we figure out that what we need in terms of the damping, additional damping to make the building comfortable and accelerations acceptable, we look at different options. So one of the options is if you have space. If you have space and there is an issue with these systems are basically, these are pools with excited when the building gets excited. So we provide these options to the client, and there's a study. There goes a study with them, and they make a decision. Sometimes we increase the building height, sometimes few meters maybe to put the tanks in there. These are much cheaper if you look at the twin mass dampers. So this is okay. So this is basically shows you a column slush tank, how it works. This is a damper in. This is a damper on top of the MoMA tower. Above this, we have a BM unit, which is a window washing building maintenance unit. So as you can imagine, this is a very special design because everything was sloping, there was no space. We also provide another alternative for 3-stack pools to water tanks, but the ownership wanted to go with this because of the space they wanted to have. Here's another detail. So this is shows you how it works in each direction. This is when it's under construction. So this is not necessarily has to be steel. Sometimes we do buckets, so it means that there's a steel bucket and we place concrete in there. Again, this is something that we discussed with the team, which is going to be faster because these items has to be lifted to the top of the building, and having a crane holding up a crane for a certain amount of time is extremely expensive. in New York. So in this one, we have buckets filled with concrete. The ownership was okay because they wanted to pour it with the other structural members, concrete members. This is a TMD view of TMDs in 432 Park. We have 2 of them, and because of the space requirement, we couldn't have one, and the core goes in between. This is the time it was done. It was the biggest tube-mesh damper. So this shows you how this in action in each tube-mesh damper. So this has also concrete, steel bucket and concrete fill material to save money. So there are different designs for tube-mesh dampers, but there's tube-mesh dampers 2004 to 2000 up to this year. The number of the dampers in that 15-year range double, especially in New York. The number of them is just double because of the need of them, because now we have a lot of data, we understand how they work, and our systems are much inclusive now. And so we use this as a tool where we need it. So basically, this is the acceleration criteria. We look at it. This is this is ISO criteria 1 year, and this is North American criteria for 10 years. This is residential and this is office. Also, we look at the 1 month criteria as additional. This is another damper. This is 111 West 57th Street. This is a special damper also. Again, we have space issues, as you can imagine. This is at the top of the building, and we have just a detail. You have 2 sets of masses in there. This is this destabilizing mass. This is the main mass. You try to achieve a longer period of the buildings. This is basically some data. You see how effective dampers are. You see when they present dampers in action after they commission. You see the dampers' effectiveness. This is a data that, so what happens is we have our consultants, say wind tunnel and damper designers, they heavily depend on the information that we have. So it's very important to understand how your structure is going to behave, what to expect the time of the construction, what to expect after a major storm. So this shows you it's around our structures, and which means how we calculate them, and at the end of the day there are real measurements before they commission the dampers. It's close to 5% range. So we are able to we have an understanding to reflect into the field that there's going to be around 5% difference in what's expected to behave and what's in the real field. This may be a major issue. Sometimes you see buildings, they finish after they say the engineer says there needs for damper. They do the calculations, they do the measurements, and you see there's no need for a damper. Sometimes it can be opposite. So what's important thing is in this, you have to understand the materials very well. You have to assess the information very well, and you have to observe the structure through the construction. Every project of us we know every floor what the concrete strength pour, what does it come out of the tests. Not only concrete strength, we also look at the MOE, everything. So we have extensive data, and we hold this extensive data to understand the structure. So that's it, basically. Thank you for your time, and I hope you enjoy. And I'm happy to take any questions if there's any. Thank you.
Thank you very much, Fatih. Vamos abrir para perguntas. Quem quiser, por favor, levante a mão. O microfone vai até você.
Hello, Fatih. Thank you. Congratulations for your lecture. Ok. Uma curiosidade. Como é feita a avaliação das vedações da interface com as estruturas, não só do ponto de vista de esforço lateral, vento, mas também do ponto de vista de deformações, se isso é levado em conta desde o início do projeto, o tipo de vedação e essa interface, se existe algum projetista, inclusive, dessa parte. Obrigado.
Yeah. So, what we do in our projects is we issue a detailed memo to the client. We tell them what to expect in terms of the deflections, and also facade consultant has this information too, to make sure that facade works with them. Deformation on these buildings are very important because once you have the starting to have the slender building, the deformation character changes. It's not a pure shear deformation. There's a big bending component into this too. So if you don't address it at the early stages of the project, this may be a very big monetary effect. Also, by code, we have to address in New York what you call the seismic gap. So we have to provide a gap between the buildings. So that one, we also provide detailed calculation to the building department, and they go to the building calculations to make sure that there's enough gap between the buildings, this one. And the other thing is the facade is very important, right? Also, with the creep and shrinkage, we address how the building facade, how the exterior of the building is going to deflect vertically, right? Sometimes you have an eccentric building, eccentric structure, the stiffness eccentric, right? So we try to control, we have to understand, because it's very hard to, if the building is just because of the gravity starting to move in horizontal, right? Because you have to understand that, what kind of impact is that? Beforehand, we try to address it by changing the thickness of the materials, redistributing the capacities, right? In MoMA Tower, what we did is, since the core is eccentric, whatever the facing to the outside, we reduce that wall thickness and add to the wall thickness to the inside, where is the more gravity loads, just to control the horizontal. This can be an issue with plumbness of the elevator, if you don't address it at the beginning of the project. And along the project, it's the elevators may not work, So there are a lot of components come to these buildings. When we, it was, I guess, it's just 10, 15 stories, 20-story buildings. It's not an issue, this kind of stuff. They have the same memo for 10, 20 years. It says, add this much to columns, add this much to the floor, so when everything goes down, there's the leveling, right? I'm just saying it was a deflection-wise, just information, how much information we provide to everyone. So then now this is not enough anymore. There's a lot of, if you don't address it at the right time with the right people, and when we first started to addressing this there was a lot of questions because the other side, the contractors and the other consultants, they didn't understand the situation because they never faced this thing, right? But you have to understand that this is the first time you're going to 1,400 feet, 500 feet, 400 feet, and these are all residential buildings. It's not, you cannot keep the same kind of criteria, you cannot. So, but now they're on board because you see that the level of information they're asking from you is changed too along the line. When we first get our buildings and we try to tell them, look, this building is going to move, there's a plumbness, the code doesn't address the plumbness anymore. You cannot do the same thing. It's not going to work, This is how much you should expect to work. The facade, we tell them, look, the time you put the facade in there, this building is already deflected this much. Then it's going to keep deflecting with the creep and shrinkage, right? So you have to make sure that you take into account of this thing. Sometimes they do corrective measures.